Edexcel Core Pure, second order differential equations 3, modelling with second order differential equations, the simple harmonic motion. So we're going to look at simple harmonic motion in quite a bit of detail here, and a classic example of this is a mass which is bouncing up and down on the end of a spring. So if you have a spring which is fixed at one end and it attached to a mass and the mass is moving, there'll be a tension in the spring, there'll be the weight mg, but the mass is moving away from an equilibrium position. And the important thing here is that if we look at the displacement from the equilibrium position, which I'm going to call x, and we consider the acceleration, the downward acceleration, which is d2x by dt squared, then it is true that this downward acceleration d2x by dt squared is proportional to the displacement and in the opposite direction. So in other words, the bigger the displacement, the more that the mass will accelerate towards the equilibrium position. It's always trying to accelerate towards the equilibrium position. Even if the mass is above the equilibrium point, then the spring is compression and it will be pushing it back towards the equilibrium position. So this is a really important property of simple harmonic motion. We get a similar effect if we look at simple pendulums, and if we look at something like a piston inside an engine. The piston is always being forced back to the equilibrium position by the small explosions within the chamber. So all of these and many other real life situations can be modelled as an oscillating motion and modelled using the equation d2x by dt squared is minus omega squared x. So there we can see the acceleration is proportional to the displacement and it's in the opposite direction to the displacement. So taking this classic equation for simple harmonic motion, we can see that it is second order, and if we rearrange it slightly to get d2x by dt squared plus omega squared x equals 0, we can see we can write it as a second order linear homogeneous equation, and therefore we could try x equals a e to the mt and get the auxiliary equation m squared plus omega squared is 0, m is plus or minus omega I, so here m is imaginary, and therefore we can write our complementary function, or general solution in this case with it being homogeneous, as p cos omega t plus q sine omega t. And we've seen in core maths that we can simplify expressions like this. We can actually simplify it using things like r sine theta plus alpha. We can get the form of this problem and make it a little bit easier for us to handle. In other words, we can rewrite this as x equals little a sine omega t plus epsilon. In other words, we have an oscillating trigonometric function that will have an amplitude, and omega and epsilon will determine its period and phase shift, as we will look at in a moment. So we took this second order homogeneous equation, we found the auxiliary equation and its imaginary solutions for m, and that gave us the general solution, and then using this little bit of core maths we were able to simplify it down into this very, very convenient form, x equals a sine omega t plus epsilon. So now if we look at this general solution in a little bit more detail, I'm going to use a bit of notation here. For example, when I talk about dx by dt, I can call that x dot, and d2x by dt squared, the second derivative, can be referred to as x double dot just for convenience. So if I now differentiate this with respect to time, I can write this as x dot is a omega cos omega t plus epsilon. So that represents the velocity of the mass, and if I differentiate again, I get x double dot is minus a omega squared sine omega t plus epsilon, and I can now replace the a sine omega t plus epsilon with the original x and say that x double dot is minus omega squared x. So that is back to our definition of simple harmonic motion. And don't forget, if we're talking about, for example, a mass on a spring, then the force acting on the mass, the overall force, would be proportional to the distance from the equilibrium position and acting in the opposite direction. So now we can talk about the period of this oscillation, this oscillating system, and the period, the time for one complete oscillation, is defined by 2 pi over omega. So omega determines the time for one complete oscillation, and we can also talk about the phase shift. So the phase shift is the shift that we will see for this oscillating sine wave. So for example, if we set omega t plus epsilon equal to 0, knowing that sine of nothing is nothing, so x would be 0, and if we rearrange this for t, we get t is minus epsilon over omega. So when we look at the displacement time graph, for example, it would have a phase shift of epsilon over omega to the left. So we can talk about the phase shift of the graph, and we can talk about the period of the graph, how often the graph will repeat. In the next video, we're going to be looking at the next stage of this, which would be damped simple harmonic motion, but in a moment we're going to be looking at these characteristics using a GeoGebra file. So here we can see x equals a sine omega t plus epsilon, and at the moment I've set a to 2, omega to 1 and epsilon to 0. So we are currently looking at x equals 2 sine t. So the amplitude A, as you would expect, determines the highest and lowest values of x. So if I just leave A at 2 for now, if I change omega, this changes the period of the graph. So at the moment we're looking at x equals 2 sine t, and if I increase omega to 2, we can see that we get to x equals 2 sine 2t. It's got twice the frequency. One complete cycle isn't 2 pi anymore. The one complete cycle is pi. So that's 2 pi divided by omega, which is 2, gives us one complete cycle is pi. If I go back to omega is 1 and we start to adjust epsilon, as I increase epsilon we can see the graph going backwards. So if I make it 1, and you can see that the sine graph we had a moment ago has moved backwards by 1 unit of time. So now if I change omega and epsilon, so let's set epsilon back to 0, I'm going to make omega 2 again, so we can see that reduction in the period. It's now pi is the period of this graph. Now if I increase epsilon to 1, you can see that the phase shift is only half a unit of time backwards, because the phase shift is epsilon over omega, so in this case we got a phase shift of half backwards. So in summary, this is our definition for simple harmonic motion. Notice the acceleration is proportional to the displacement but in the opposite direction. Once you've got this standard definition, always try and pick out omega, because you can then write your simple harmonic motion equation as x equals a sine omega t plus epsilon. So this is an object oscillating about the equilibrium position. So we know that sine theta is bounded by -1 and 1, therefore x is bounded by -a, and of course a is the amplitude. Sine t, if we just had a simple sine t graph, then that would have a period of 2 pi, and therefore this graph, which has a sine omega t plus epsilon, would have a period of 2 pi over omega. And the phase shift is the translation effect that you get for your trigonometric graph, and you can find the phase shift by doing epsilon over omega, and if it's positive it will move to the left. In the next video we're going to be looking at damped oscillations.